Good afternoon, everybody. I'd like to welcome all our guests. I see a few people that aren't members of the Middlebury Garden Club who have joined us this afternoon. We're all very excited to have Dr. Alan Betts here to speak to us today about climate change in Vermont and in general. He has a PhD from the University of London in the field of meteorology, but has lived in Pittsford for the last 30 years or so. He has been involved in both regional and global weather research and has been funded partly by NASA and the National Science Foundation. He's received many awards and has a resume too long to cover here. But anyway, we're thrilled to have him. He also writes a column in the Sunday Rutland Herald on environmental issues. So without further ado, I present Dr. Alan Betts.
That everyone is following on this planet, the melt of the Arctic ice cap. About half the ice cap melted in 2012. This is a schematic looking down the pole. Here's Greenland. We're down here somewhere in the northeast. Here's the Hudson's Bay. The end of the melt season in the Arctic is mid-September. This purplish line here is the coverage of Arctic ice at the end of the melt season in the historic period, the last 20 or 30 years. And it varies from year to year. But we hit a new low here. Not only is this now much smaller than it used to be, it's also much thinner because much of it only lasts from 1 or 2 years. It plays a role in the Earth's climate because ice, sea ice, floating on the water reflects sunlight in the summer at the Arctic season. And also ice on the water, as opposed to open water, ice doesn't evaporate like open water does. And the water, when it evaporates from the ocean, puts water vapor into the atmosphere. And water vapor is a very strong greenhouse gas. So more evaporation means more water vapor greenhouse. Less ice means less reflection of sunlight. Now, those are exactly the same processes which are giving us a cold winter this year with lots of snow versus the very warm winter we had 2 years ago in 2012. And this also affects us locally. If Hudson Bay freezes much later in the fall, like it did in 2011, it means much less cold air comes down and we get a warmer fall. Scientists map things out. I'll just show you a few graphs, but this is the ice extent in the Arctic in February when it's at a maximum, and in September when it's a minimum. And you can see this rather steep decline is about 12% per decade, and we're dropping below that straight line. It's a problem for us as scientists because this graph here shows an average of a bunch of models predicting how much out to the end of this century, this is 100 years here, how much the sea ice is expected to decline, with a sense of the uncertainty. And these are the same observations put on there on the same scale. And the sea ice appears to be melting faster than our models, meaning that the processes here are amplifying faster. It's not just ice that's shrinking in the Arctic. Snow there takes much longer than here in Vermont to melt, so there's still snow cover in June in the Arctic. This is a measure of what's called the anomaly, how much less it was than average, and this is the same thing. And you can see over the last 10 years, here's 2004, there's been almost a continuous decline in the amount of snow around the Arctic in June. Snow does just the same thing as sea ice. It reflects the sun. Now, I've been, as it happens, been doing some work very recently because Canada sent me all their Canadian prairie data back to 1955. And this is an average for Saskatchewan, one of the central prairie provinces. And it just shows you how much temperature drops with snowfall. The 50 years there have been averaged so that snow starts on this day, and this is, so we go from no snow to a lot of snow. It's in centimeters, it's just a few inches in fact. And the date of that first snowfall here is about November the 15th. And across a few days, on either side of that snowfall, the temperature drops about 10 centigrade or 18 Fahrenheit. That's the climate change with snowfall in the fall, and this is the slower melt of snow in the spring until there's none left, and once again the temperature comes up 9 or 10 centigrade, 16, 18 Fahrenheit. Snow is the same reason as what's happening to the Arctic. Snow reflects sunlight. It acts as a climate switch when we get snowfall. So watch it when we get another lot today. I mean, we're only seeing a single example here, and there's lots of weather things going on as well. But today is 45 degrees, and tomorrow with snowfall, the rest of this week's going to be chilly, because the snow reflects the sunlight, even though it's March. It also reduces the evaporation, and that reduces the water vapor in the atmosphere. It changes our local climate. On the very long time scale, this is looking back the last 1,000 years. The black line here is an estimate of the global temperature for where we have real thermometers going back barely 150 years. And these are what are called proxies, from treelings and corals and stalagmites going back the last 1,000 years. And there was a cold period, we call it the Little Ice Age, and a warmer period earlier in the last millennium. These have been important to human history. I mean, we could grow grapes back then in England, where I came from, and when the Pilgrim Fathers landed in 1620 on the bitter winters of the Little Ice Age, they would have been wiped out if it hadn't been for the help of the native peoples who were used to living through winter. The last 100 or 130 years on this graph, we have real observations, better as we get forward in time, and we can plot each of these points here is an average temperature on the globe. And you see lots of ups and downs early in the century, a fairly steep rise from about 1970, 1980, and it's been flat for the last 10 years on a global scale. There's all sorts of other things going on. There's problems with the data in wartime. There's problems with aerosols after we industrialized after World War II, which we think contribute to this. And we think a lot of heat is being stored in the Pacific Ocean at the moment. And the next time we get an El Nino, this temperature will take another jump. But for reference, this is only 1 degree Fahrenheit. Our models predict that if we stay on a fossil fuel intensive path for all our energy system, as we have done for the last 50 or 100 years, mean temperature of the planet will go up about 5 Fahrenheit, 5 times this by the end of the century. And in the north and in winter, it will be more than that. The primary driver is the rise of CO2 in the atmosphere that's coming from the burning of fossil fuels. And some very forward-looking person back in the late 50s decided to measure this continuously on Hawaii, on Mauna Loa. And you see this strange up and down spike, up in winter, down in summer, and a steady rise year to year of about 2 parts per million. If we could take this thing back, it was about 280 parts per million for much of the last 10,000 years. Now, why does it go up in winter and down in summer? This is not a test. This is just... Any answers are acceptable. Yes?
Fewer plants.
Fewer plants. CO2. It goes... The flip side of that, it goes down in summer because all the plants and forests and crops in the northern hemisphere suck out CO2 during the summer. The reason it goes up in winter you don't think about, because when they're not doing that, everything that is a living respires, essentially uses oxygen to metabolize food and breathes out, either through its pores or me through my lungs, carbon dioxide. So in the winter hemisphere, CO2 comes up. And in the long term, we were to go back in time here, these were in balance. They're not in balance anymore because of the very large amount that we're putting in from burning fossil fuels. And we keep track of that. This is, I think, billions of tons of fossil fuel emissions, and each of these dots is each 1 year. And this little drop was the great catastrophe from our perspective in 2009. What was that? The Great Recession. Our emissions of carbon dioxide actually decreased that year. and they're back on this curve here, increasing again. And these reference lines are what are called emission scenarios that have been used by the IPCC that does these global climate reports to estimate out for the rest of the century. To put this in reference, what we viewed as an economic catastrophe, this little downturn, if we are to stabilize CO2 in the atmosphere, we have to go on this path, about a 4% reduction for the next 30 years. And we're back on this path. And so you understand immediately what a challenge this represents for us. Couple of things on the big picture before I move on. This is the same curve, the total emissions of CO2. This is how much ends up in the atmosphere, which varies a lot according to whether it's dry or wet in the tropics. About half of what we are burning is being taken up by the oceans and forests. And that is, of course, hugely beneficial to the climate of the planet. The other big picture thing you need to understand is it takes at least a century or so to remove CO2 from the atmosphere, and many centuries to remove it from the oceans, where it has to be dropped out as things die and form layers at the bottom of the ocean. Now, what goes into the ocean is a problem in itself, completely different from what's happening to our climate system. When CO2 dissolves in the ocean, it produces a weak acid. We call it carbonic acid. Now, that doesn't matter to you when you drink a soda that's got CO2 in it, but for all the things in the oceans that take calcium, these are little things called coccoliths, this is a bit of coral, that's a sea urchin, that take calcium out of the oceans, they can't do it when the oceans become less alkaline, more acidic. And as CO2 dissolves in the water, the oceans are becoming more acidic. They're moving in the acid direction. And we know that by late century, there's going to be a grand transformation in life in the oceans. It's something the oceans have gone through in the past, meaning hundreds of millions of years. It's not something we've ever seen, and it's, of course, going to impact our fishing at some point. Why is carbon dioxide a problem? Well, a little bit of global energy balance for the planet. The air is largely transparent to sunlight, and that's how it keeps the Earth warm. But the gases in the atmosphere, some of them trap the Earth's heat, radiate it back down, and they also keep the Earth warm a lot. That's a centigrade temperature, but think 55 or so Fahrenheit. Those greenhouse gases, as they're called, are water vapor, carbon dioxide, ozone, methane, and a bunch of others like the chlorofluorocarbons we used to use in refrigeration. Now, the one that's being driven by burning fossil fuels is just CO2. It's not the most important. Water vapor is the most dominant. And if it was just that problem, no problem. The trouble is that as carbon dioxide increases, there's lots of feedbacks in what we call the water cycle. The very big one is that the Earth gets warmer, and then evaporation and water vapor increase. That roughly triples the warming that comes from carbon dioxide alone. And the second one, we've mentioned both of these already, as the Earth gets warmer, snow and ice decrease. Less sunlight is reflected, and that means winters in the Arctic are warming much faster, something like double as fast. We estimate that the Earth as a whole, if we double carbon dioxide in the atmosphere, will warm about 5 Fahrenheit, but it will be much more in the north, overland, in winter. And the climate change that we're seeing in Vermont is likely to continue. Well, I could go down this path, but it gets gloomy too fast. There are lots of things, extreme weather which is increasing. We're seeing big increases in weather disasters. There are things like the release of methane from the Arctic as it starts to melt. And of course, there are a lot of ecosystems on this planet which are now threatened because they can't adapt fast enough. And we are one of them. Our human population may be unsustainable this century if we stay on our present energy path. But before we get down that path too far, because a lot of it is unknown and unforeseeable in detail, I'm going to map out what you're familiar with, what's been happening to Vermont in the last few decades. Well, here's the snapshot summary. It's been warming twice as fast in winter on average than summer, but our winter minimums have been going up much, much faster, and that's critical from a gardening and growing shrub perspective. We have a marker like the Arctic ice, there's a reference lake I'll show you in a moment. It's frozen, number of days it's frozen has been shrinking 7 days per decade. The growing season between frosts has been going up a few days per decade, spring coming earlier 2 or 3 days per decade. This is kind of easy to understand, and I will show you that in some detail in a few slides. But something we were not fully expecting has been happening is extreme weather has been increasing. And that's being driven by one thing we know well, which is that evaporation goes up quickly with temperature, but also the patterns of weather on the globe have been becoming more stationary, like this winter, for example. And I'll come back to that also. So here's a little graph, centigrade on the left, Fahrenheit on the right, summer. Each dot is a point is a June, July, August average summer temperature back to 1960, and that upward trend, a lot of variation you notice, is almost half a degree Fahrenheit per decade. Same thing for winter. The range of temperature here is the same, even though it's colder. Winter is going up about twice as fast, and the variability is much larger in winter. The variability is probably related to how much snow cover we had, and this steeper rise. Just think of winter is warming twice as fast as summer. Now here's this couple of reference lakes. The Eye on the Sky people, in their wisdom back in 1970, trained an observer to estimate the ice out date and the ice in date on Styles Pond up in the Northeast Kingdom. It's not far from Joe's Pond, for which there's a competition just for the ice out, and some of you I see are familiar with that. And you can see they're very similar. So this is every year, and this is just back to 1971, I think, the first data. And I put on some trend lines. Freeze up in the fall is coming about 4 days per decade later, ice out in the spring 3 days earlier per decade. And we subtract those two. This is the number of days Styles Pond is frozen, and there's lots of variation from year to year, but that trend line is a decrease of the frozen period 7 days per decade. And you can think of that also as being perhaps similar to the number of days that your garden soil might be frozen in winter. We also keep track of, in the United States, the date at which lilacs leaf out and bloom in spring. So this is again days of the year, and I didn't show you, well, let me see, this is the beginning of, where's the beginning of April? Here. Lots of variation from year to year. The trend there on leaf out is again 3 days per decade, and that huge variation from year to year does mean something that you can easily understand. If we plot the day of year when lilacs leaf out against a temperature in the preceding months, we get a nice tight relationship that basically says that for every degree Fahrenheit it is warmer, lilacs will leaf out about 2.5 days earlier. And it's the same for bloom, which occurs later. Bloom is not moving as fast. We have 3 days for what this is. We think of this, phenologists, people who study these leaf out dates, think of this as early spring, and this in May, for the bloom date of lilacs, the beginning of May, as being later in spring. The slope here is less, but this relationship, for every degree Fahrenheit that it is warmer, in this case in April, the lilacs will leaf out 2.5 days earlier. And in fact, the same thing is true of the lake that I didn't show, the ice out on the Styles Pond. And we can plot up everything. People keep track of maples and when they leaf out, which is the purple line here, and earlier stage of leaf, and they all go together, and they all have this 2 or 3 days per degree Fahrenheit change in the spring. Winter is so important to us in terms of understanding our climate that I'm going to show you a number of examples of this. This is just looking across the Otter Creek from my vegetable garden is behind me. And you can see very reflective snow that's lying on the mowed hayfields. Down there's a covered bridge on Otter Creek you can't see. And you can see the snow shades. The trees shade the snow in the foreground there, just as they do in the dark background. When there's a forest, the reflection by snow is much less. When we have a very warm winter like 2011 to 2012, the snow melts. This is a positive or amplifying feedback, and it stayed warm that winter. This year we've had locked into a very snowy patterns over North America in the east, and it stayed cold. But let me say a little bit about hardiness zones. You as gardeners are very familiar with them, and this is an estimate put out by the National Arbor Day Foundation of how much the hardiness zones changed in just 16 years from 1990 to 2006 across the Northeast. Vermont used to be mostly Zone 4, with a bit of Zone 3 in the north, Zone 5 in the south, and more than half of Massachusetts was Zone 4. In just that 16 years, much of the Massachusetts is now Zone 5, half of Vermont is Zone 4, I've got those mixed up. Now, most of Massachusetts is Zone 6, meaning the minimum temperature doesn't drop below -10 Fahrenheit. Much of Vermont is Zone 5, and the Zone 4 region has shrunk. Yes, I got that right this time. Now, that's a very big change. This is a kind of rough map. I hit something there. If we go to the actual map you would find on the USDA site for Vermont, it's a very complicated picture because it shows the mountains and there's subzones 4A and 4B and 5A and 5B. But if you think about what I was just showing you, if we've moved, each of these zones represents 10 degrees Fahrenheit change in the minimum temperature. What was your minimum temperature this past winter on your gardens? -11. Any other offers on -11? -15. Someone hit -14, -20. All those values are still 10 degrees warmer than what Vermont used to reach. And that is a whole climate zone. And if you think we are moving a half a zone in 16 years, one climate zone in 30 years, it means we're moving 3 climate zones per century in Vermont. And we've moved 1 roughly since I started gardening here. That's a big change. Southern Vermont down here is already in Zone 6. And there are lots of other graphs you can plot up. I mean, this is just an aside here. The number of days below 0 degrees Fahrenheit is a popular one with the forecasters. And this is the decline in that number of days in Burlington. It goes up and down from year to year. And this year will be a high value for Burlington. But the trend line is very strongly down. But here's my second test. Southern Vermont's becoming Zone 6, means we can now grow hardy peaches. It also means more pests are surviving the winter, and this has a health impact as well as the ticks that you're familiar with, and I'll come back to that briefly later. But I wanted to test you on this. This is growing in my garden. It's October 1, not last year, the year before. What is that little?
That's an avocado.
It's an avocado. Surprising how many foresters can't get that right. They don't think of avocados growing in Vermont. It is an avocado. It was killed by the frost. But if we're moving 3 climate zones per century, by the end of this century on our present path, you'll be able to grow hardy avocados in Connecticut. But the flip side of that is what's going to happen to our hardwood forests. They're not used to growing alongside avocados. The way I keep track of winter as a gardener is by when I can turn over my rye cover crop. So this was a really exceptional winter a couple ago. I was still able to dig, no frost at all, until the 2nd of January. And I show these slides because I started gardening in the late 70s in Vermont. And if someone had told me in the late 70s I would be digging over my cover crop in January, I would have simply laughed at them. I would put my shovel away in probably mid-November and not get it out till mid-April. We used to have about 140 days of frozen ground. That was such an exceptional year that by today's date, notice it's March the 11th, 2012, I was out there digging again. That's only 67 frozen days. We had no permanent snow cover west of the Greens, and it was in contrast there with a snowier winter the year before. And this tiny map in here You can barely see it, but these dark reds, there's a number 117 on them. They say that from the Dakotas to Maine, that 6-month period, through including winter, October 11 to March 12, was the warmest in the 117 years that we had on record. Now, when I look at that and I say, what was happening across the Canadian border? One of the strange things in our climate world is the Canadians see this, and we see this. And we never see both. But in Canada, it was 12 Fahrenheit warmer for in this case, the 3 months of winter, which they produced a map for. And warm all the way up through Canada. This was a huge North American warm season that year. Very sharp contrast to 2 years later, where we've had the flip side of this. This year, it was very warm in North America and very cold in Europe. Sorry, in 2012, it was very warm in North America, very cold in Europe. 2014, very cold in North America and very warm in Europe. Massive flooding across storm after storm in the Atlantic, affecting Britain. That particular year, it hit 79 in a couple of weeks. On March the 22nd, my daffodils were out, my forsythia was in bloom a couple of days later, and for gardeners it was amazing, except we did get a little bit of a frost, I think, later. I put up the next year because it seemed to many people that it was a little bit snowy. This is last winter, but in fact, ground did freeze up on December the 21st, and we got a serious snowfall around Christmas. But the ground thawed again under that snow, and here I am on January the 15th, 2013, and I'm digging over my cover crop just to make the point, you see. And in fact, final melt last year was again March the 11th. We had much more snow than in 2012, and it kept melting. I will produce one for this year, but I did check before I came to give this talk. My ground is certainly frozen March 11th this year. First and last frosts are different from winter minimum temperatures, which really affect how deep the frost goes into the ground, and they affect what will survive the winter in terms of shrubs and crops. First and last frosts are those nights in the spring and the fall where a clear sky, dry sky, the earth can cool to space. So they're single night events. And this is the date of the last freeze in the spring and the first freeze in the fall, and the difference between them when we think of the growing season or the time when frost is likely. And you can see, just looking at that, lots of variation from year to year, but the general trend in extreme years is towards convergence. The growing season is increasing 3 or 4 days per decade. And that, of course, has been a great help for the local food movement. But the rise in the winter minimums have been an even greater help, because now under unheated greenhouses and row covers, which each give you like another climate zone improvement, you can winter over a lot. I've been wintering over kale, particularly the last few years. And I'm trying, even this year, I have it in a cold frame, frozen up with ice, and we'll see. A couple of things just about this frost concept. You're familiar with this. I'm just going to turn it into something a little more quantitative. Here's a typical date. Used to be, think, mid-April. It's been shrinking. I don't know when it'll happen this year, when the daffodils are coming out. Before the leaf out of the forests, blue sky, dry sky, low humidity. This means little water vapor, a low water vapor greenhouse, so the earth cools a lot at night. Very large range of temperature between the maximum and the minimum, warm days, cool nights, and frost. Once the forests leaf out, we go from very little evaporation to very large evaporation within a week. And then we have a wet atmosphere, often with much more cloud, much less cooling at night, cooler in the daytime. We can actually get a cooling from before and after leaf out that's quite substantial, and a much less chance of frost. And as the spring becomes earlier, this transition in the climate in spring is moving earlier by about 3 days per decade on average. And something like the opposite happens in fall. You can think of this, that the vegetation, the forests which are evaporating water, are postponing the date of that first killing frost by putting water into the atmosphere. But they can only do it so long. While they're evaporating, the air stays moist. But some cold night, dry air will blow down from the north, where the forests are already have shed their leaves, and we'll get a dry, cold night and a hard frost. And then the vegetation, if it just shuts down, it knows that winter's coming. It's one of the many signs it has that winter's coming. It also tracks the length of the day. And as with many of the last few years, that first fall frost, killing frost, has been coming later and later. And often the forests start to dry down and the leaves turn brown with less color as a result. This is another piece of work I've been working on. And I should say the reason I'm putting some of these figures in, even if you are not following them all, is that this talk is on my website, alanbetts.com, so you can pick them up for reference. But this is the difference, this is what clouds do to summer and winter climate. And this is summer, and it's again some data on the Canadian prairies, and this is cloudy, 95% cloud, and this is clear, 5%. And the maximum, this is just the diurnal range of temperature, and local noon is here. And this just shows you the maximum temperature goes up quite steeply as the cloud cover goes down. But the minimum temperature in the summer doesn't change much. And that's completely the opposite of what happens in winter. When it's cloudy in winter, it's warm. And as it gets clearer and clearer, and this is the almost clear sky case in winter, the temperatures plunge. And the minimum temperatures plunge the most. This is because in summer the clouds reflect the sunlight, and that's the dominant process. And in winter the clouds stop the Earth cooling to space. The clouds are a greenhouse. And you're familiar with those, but you probably didn't appreciate just how stark it is. And in fact, you can go from this kind of relationship to this one in just 5 days with fresh snow cover. When we look ahead for the rest of the century, scientists run models. And this is one to try and give you a visual sense of what will happen to Vermont's summer climate in terms of the climate of the end of the last century by the end of this century. If we stay on a business as usual fossil fuel economy, the climate of Vermont will be similar to the climate of Georgia at the end of the last century. Whereas if we make an effort, make our society much more efficient in energy use and shift to renewables, it's going to be still maybe southwestern Pennsylvania. And you as Vermonters have a good sense of what that difference is. But to tell you a kind of funny anecdote, I gave this talk once in Vermont and then flew down to Atlanta, Georgia, and gave this talk at Georgia Tech the next day. And those Georgians, the first reaction was to laugh. They said to me, well, those Vermonters will have to get used to Georgia's climate. What was the flaw in that argument? What's going to happen to Georgia? They were in the middle of one of their worst droughts. There was a silence in the room. You could see the lights coming on. What's happening to Georgia and the southern United States, and this too is going to affect us in Vermont, is that they're moving into the drought subtropics. Not every year, but on average, as time marches on into the future, it's becoming more droughty down in the south. You remember that big drought in 2012 across the central US, droughts in Texas. This year the drought has only been in California. So this transformation is not just a local picture here for Vermont. It involves something for the whole of the rest of the US and the world. Now I'm going to say a little bit about extreme weather because this is affecting us a lot. And you have to understand that because this is not a climate system that's moving slowly in one direction. It's moving with lots of increasing extremes. Rain, precip as we cheerfully call it, comes from the condensation of water vapor when it flows through cloud base. An enormous amount of heat is released when water condenses. I hope you've never put your fingers into steam and burnt yourself. You learned not to do that when you were a child. But it takes a lot of energy to evaporate water, and you get it back when the water goes through cloud base and condenses. And that's the energy that drives storms, thunderstorms, hurricanes, everything that has water condensing in it. The vapor pressure of water, what we call the saturation vapor pressure at the base of clouds, goes up very steeply with temperature, 4% for every degree Fahrenheit. And that's driving the intensification of storms, but only in a very familiar sense. You know that summer storms have much more intense rain than, say, cold snow that falls in the middle of winter. And the warmer our summers get, it's more as if the tropical rainfall is moving up into Vermont. But what's been happening is that the pattern of the very large-scale flow, the jet streams, the frontal patterns, are becoming more stationary. And that means we're getting longer rain events or more frequent rain events. And that gives us regions of lots of drought and lots of rain in different areas of the world. And that's happening on a very grand scale. As I think I mentioned it earlier. This winter we were frozen into this cold Arctic vortex patterns across the US. But in the Atlantic it was much warmer, and in Europe it was much warmer. And storm after storm developed in the northern Atlantic, dumping massive amounts of rain on Britain. And some of the storms were so large that they drove waves up on the West Sea that were 50 feet high, essentially close to records. We don't really know what's driving this shift in the climate, but we've been seeing it for about 10 years now, and along with it comes lots of extremes. Heavy rainfall is increasing rather strongly across the Northeast, but I wanted to just illustrate with something you're familiar with, the floods we had in 2011. We had two floods in Vermont. One was the spring flood on Lake Champlain, and which was associated with record spring, warm spring temperatures, record spring rainfall, and the melt of a significant snowpack. They all contributed to that. And then it stayed wet during the summer, and then we had record floods with Tropical Storm Irene in the fall. But if you step back and look at the United States as a whole, this is a map which shows you the ones here for Texas and New Mexico mean that those two states had the driest 6-month period on record. We have a record that goes back, in this case, now 117 years. And from Ohio to Vermont was the wettest 6 months on record. So yes, we had two floods, but they were within a pattern across the United States in which many, many storms dumped rain on the Northeast and almost none dumped rain on Texas, even though the governor was praying for rain. So here we have a quasi-stationary pattern, and within that two extreme floods. And it mattered to us. If we had not had that wet summer, Irene would have done nothing like as much damage. We've had similar tropical storms go by after a dry summer, and the ground then absorbs the first few inches. One of the things that's been happening is these jet stream patterns have been becoming larger in amplitude, and you can hardly see the US on here, but there's Florida, and somewhere under there, there's Vermont and New Hampshire. Alaska's up there summer, and this is a map for the 1st of July last summer. The end of a couple of week period, this pattern had just sat in there. And in June, some of you will remember, we had some rather severe flooding in central Vermont. Alaska was enjoying 90-degree weather. Death Valley was enjoying close to 130, and Vermont was enjoying rain after rain. And something similar to this with these cold vortices, with this pattern a bit further west and cold air plunging into the US, has happened a lot this summer. When Sandy came by a year later, it was another of these high-amplitude jet stream patterns bringing cold air down from the Arctic. Sandy came up and was sucked into that pattern. The pattern was stationary because there was a high pressure here off the east coast of Canada, and it was sucked in. There were actually a couple of feet of wet snow in the Virginia mountains, a huge storm surge, And the combination of the storm surge, the high tide, and this jet stream pattern and the hurricane all led to a disaster in Manhattan and New Jersey. So we're just going to have to shift tack because time is moving on. What lies ahead? Well, this is not a particularly pretty slide. Accelerating change and accelerating extremes, increasing adaptation and rebuilding costs, and environmental damage that will transform or destroy ecosystems locally and globally. And the underlying problem is a very simple one. We dump all our waste streams from our industrial society either into the atmosphere, think CO2, the streams and the lakes and the oceans. Some of you, I'm sure, have seen all the piles of stuff that's piling up in the oceans, primarily plastics. Lake Champlain is suffering from too much phosphorus flow from farms and from human effluent. And from the atmospheric point of view, we just can't go on dumping CO2 into the atmosphere without paying the consequences. And the scientific community looks at this and says, well, you're going to have to change the economic system. We're going to start having to have waste taxes, like fossil carbon taxes, tax on other forms of waste, because they will encourage people to change. We use this word mitigation, but they're also going to be needed to pay for the long-term adaptation costs. People estimate the costs now of what we're doing to just the human infrastructure are huge, like $1,000 trillion. But the real challenge we face is something deeper. We know so much, we know what has happened, and how do we integrate it all? How do we integrate it with our society? How do we integrate it with our way of life? And how do we deal with the deep interconnectedness of life and climate on the planet? And you probably, as gardeners, have a much better sense of that than many people in our society. If I give this talk in Texas, and I do, the kind of reaction is, well, it gets warmer, we're just going to turn up the air conditioning. And if for people in a society where they drive from air-conditioned garages to air-conditioned malls, and they never really step outside because it's 100 degrees, I can understand where they're coming from, but it doesn't deal with what's happening to the Earth. So, I've mentioned this, but I'll make it explicit here. Our technology and our waste streams are having large local and global impacts on the natural world. They have to be carefully managed because we're dependent on the natural ecosystems. But that's easier to say, but it's much more challenging to do. We can't really manage the Earth. There's so much we don't know. And you can attempt to manage your gardens in various ways, but you know from year to year that that doesn't always work out. And you have to be ready to adapt. One of the things for the Earth we need is a very long time scale. But our society tends to think in a year or two time scale, if we're lucky. We need kind of new rules because human population is so great and our industrial output is so great. And the guiding rule we have used for much of the last century was simply maximize profit. And well, I'll come back to that in a moment. The localization that you see, the movements towards localizing the food supply, are very important because they give us a sense of responsibility, the ability to regain control, and they also minimize transport on a global scale. So what kind of rules? Well, we actually know what to do. And again, it's easy to map out. We have to minimize the lifetime of human waste products in the Earth system and eliminate many of the critical ones. We've only done that for one so far, which was the chlorofluorocarbons that were impacting the ozone layer. And I'll mention that in a bit if I have time. We need to maximize recycling, remanufacturing, because that minimizes waste streams and the use of non-renewable raw materials. We have to maximize the efficiency with which we use energy. We used energy inefficiently simply because we had cheap fossil fuels. Fresh water is not a big issue for Vermont, but for most of the world now it's becoming critical. And even in the United States, the aquifers are being pumped and the West is running out of snow cover and fresh water. And then we can maximize the use of renewable resources. But I need to be quite explicit that we have to maximize efficiency of energy use first, double or triple it, there's no way we can replace current fossil fuel use with biofuels or renewable energy. We can build solar facilities and wind plants, but they're never going to be enough to replace the fossil fuel use. We are inefficient because we had cheap fossil fuel. But unfortunately, we have enough coal and oil reserves to push carbon dioxide back to 1,000 parts per million. And that will melt the ice caps. And we are not willing at the moment to pay for the more costly technology, say, to burn coal and take the CO2 out at source at our power stations. And the way to put this in perspective is really very simple. No one wants to know it's very simple, but the Earth got cooler when all this CO2 was taken out of the atmosphere in the Carboniferous period, before the time of the dinosaurs. If we burn it all, it was taken out over 100 million years. If we burn it all and put it back in a century or so, we will push the Earth back to something like the climate of the Carboniferous, a hot, steamy climate with no ice caps. The ice caps are an issue because that northern ice cap that's floating is not a problem for sea level, but all the grounded ice on Greenland and Antarctica, how much will sea level come up if that melts? Does any of you have any idea? No, it's nearly 200 feet. And another figure that is, I would hope that one day every child would know, but they still don't. How much did sea level come up at the end of the last ice age, when even more massive ice caps melted? Any idea? It was 300 feet. 300 feet. And you're actually familiar with that because when sea level was 300 feet lower, and that was only 14,000 years ago, back in the memory of human, narrative, all the land bridges were open. So the people that migrated to North America migrated across the Bering Strait because sea level was 300 feet lower. When those ice caps melted at the end of the last ice age, there were massive floods. The floods that you read in the legends of the world and in the Bible as the Great Flood. That was huge, 300 foot of sea level rise in massive episodic bursts over about 1,000 years. Not overnight, over a long period of time, and a whole series of bursts within that. So, well, why is it difficult for us? Well, you probably all know this, but this is not science at this point. This is scientists' commentary on our society, and it's also a commentary from someone who grew up in Europe. The American dream is crumbling. Our economic growth was based on fossil fuels, also on debt and consumerism. You build it and throw it away, and that keeps the economy going. But it's been a disaster for the planet, and it's not sustainable. This issue I have mentioned indirectly. The Constitution here is based on individual rights and state rights. It doesn't have anything in the Constitution about the needs of the Earth's ecosystem because that was simply not an issue at the end of the 1700s. We simply pushed back frontiers and pushed out the native people out of the way, and we thought we had, it wasn't an issue anywhere on the world back then. It's a huge issue now, and we don't have a legal structure to deal with it. The other issue, which is less obvious, but because we have never tried to manage technology, is we actually have to guide and manage technology, because just inventing something, marketing it, without paying attention to the waste streams and the consequences has resulted in many tremendous successes and also tremendous catastrophes. Another reason it's difficult is simply a financial one. Our fossil fuel reserves are worth $20 or $30 trillion, going up every time the price of gasoline goes up. And so the arguments that it's unfair to the industry to regulate, it's an unfair cost to the free market, you'll hear all those arguments. And I don't really need to say anything about politics in Vermont. Our politics at a national level is lost in fantasy and largely ignoring Earth system issues. And they haven't even noticed that every time they shut the government down, there's a catastrophic snowfall or a catastrophic rain flood in Washington, D.C. They haven't noticed that. They simply, our society ignores future costs if it can. A beautiful example is that Manhattan came within a foot of flooding the subway tunnels with Irene. And they went out and designed the plugs to seal up the subway tunnels, but they didn't install them because it cost a few $1 million. It cost them tens of billions when Sandy came along the next year with a much bigger flood. Okay. I have to wrap this up. So, well, if you talk to ExxonMobil, they say it's a technological problem, technology will save us. Well, technology is critical. We have to redesign our society. But the reason it's a problem is that our technology is having a global impact on the natural world. And the natural world is alive, it's complex, and it's not under our control. And that means that our technology has to be managed, especially our waste streams. But ideologically, we've never really had to face this. I like this pretty picture. It's an illustration of the challenge that technology presents us. This is a Danish electric tricycle. It's fully enclosed, weatherproof, joysticks, fun to drive. It goes 150 miles at 30 miles an hour. No fossil fuel whatsoever. You could have a solar panel and recharge it, right? That's lightweight transportation. You might have to stud the tires in winter in Vermont, right? Okay, but this is the kind of extreme. Much of Vermont drives trucks. They get 20 miles per gallon if you're lucky, less in winter. We need an efficient transportation system. Are we going to lightweight the system? And you're seeing signs of that. I think it's BMW is coming out with a fiberglass, lightweight, totally redesigned electric vehicle, which at substantial cost. I mentioned this, and I'll just show it again. For those of you who have listened to this, regulation is bad. I want to remind you, because no one discusses it anymore, that Reagan, Bush, and Riley at the EPA, all Republicans, pushed through the Montreal Protocol and the Clean Air Act amendments over business opposition, European opposition, and they saved us all from an ozone catastrophe. If we hadn't done that, your gardens would already be impacted by the ultraviolet coming in, and we would be all going around with the Mexican sombreros and trying to stay out of the sun. People need a vote, though. People have a vote, they need a vote, and they have to be informed. So one of our huge challenges is how do we spread an understanding of what's going on to people in ways that will not frighten them, that will help them deal with the transition we face. Another slide, which I'll show you, but I also show this to high school kids. The future's not our past. And you'd be surprised, for high school kids they get that immediately. They're all ready to shuffle off the past and create a new future. But that's very hard for us older generation who've grown up with this, and for many people they are still lost in the visions of the past. I like to quote Frances Moore LePay, that some of you will be familiar with. She lives in Vermont, and she gave a talk to the opening of RAFL, the regional, whatever it is, Rutland Area Food and Farm Link, back now 7 years ago. And she said, she's the woman who wrote Diet for a Small Planet and a number of books of that ilk. She's worked on food issues globally her whole life. And she said, when I look back on my 30 years, I sum it all up with this motto: you have to be bold and humble. Bold because it takes courage to face change. And the humbleness on her part, she said, I could never have envisaged all the things that have become possible over the last 30 or 40 years in terms of the global food system when I was looking ahead. Things looked pretty bleak when she started. We know what we need: efficient society, renewable technologies. We know we have to have community impact because governments are slow with their interventions. And here's a couple of my mottos. Ask when you're faced with some choice, is this an efficient and sustainable way of doing this? And the answer in our society is usually no, it's not. But the question is, can you move in that direction? Can you foresee a path in the next 5 years where it would be more efficient? And the other is, you'll understand this as gardeners, do I have a deep understanding and connection to the earth? Because I do not think we will be able to resolve many of these issues until more of our community does have a sense of its roots in the earth. It's not something you can kind of slough off and proceed just with a human-centered vision. Health, well, this is for the health people I gave. Deer ticks are becoming a problem. Mosquito-borne diseases are becoming a problem. We won't go down that. Climate trends, yeah, I mentioned milder winters, larger variability, more rain in the cold season, more wet and mixed snow, warmer summers, heavier rain in summer. If you're a gardener, infiltration, soil, stuff in the soil to store water, all those are issues. Building soil carbon on organic matter, all the things you would do as a matter of course. We're going to have to handle phosphorus one of these days. Food, same kind of list of things. You're familiar with most of these, and I've touched on them. For us, agriculture, growing food is going to be probably improved. We can overwinter more. The variability of the weather is going to be an issue. Dealing with floodplain water and soil water management, we're going to have to face that a bit more. Summer pests may be a problem. But the flip side of this is we're much better off than much of the United States, where increasing drought and pumped aquifers is a big issue. And I think this is almost the end. We actually face re-educating our society. And all of you should view yourselves as the future re-educators in your families and in your society. There's a beautiful quote from a woman who is one of the great activists of the civil rights movement, who still lives, I think it's in Detroit, and is working on now food and gardening issues. Her name is Boggs. I don't remember her first name. She's an African American and she's well into her 90s. And she says, with that firm view of someone who's looked at this for 50 years, we are the leaders we have been waiting for. We are the leaders we have been waiting for. Don't just wait for them. Well, it's just a list of things we could look at in our food systems. The move in Vermont to composting everything, which I don't know if you know is coming in a new waste act by the end of the decade, critical. Support it. Educate people. Get all that organic waste out of the trash stream, along with recycling everything else. Rutland finally now has this one-stop recycling where now we can recycle everything, plastics 1 to 7, and everything else you just dump it in the bin, and their automatic system with lasers and magnets and things sorts it all out. Default energy use should be off. Subtle thing, but when IBM realized that up in its Essex Junction plant, it transformed them. They realized they could reduce their energy use out indefinitely into the future if they worked on that principle. And I advise everyone to reconnect to the natural world, because that's so fundamental if we're going to accept this transition that we face. I'll stop these, and because I've talked for an hour, so let's have some time for discussion. And you speak your question, I will repeat it because we're on camera, but don't be shy. Yes.
I'm just wondering if you can talk to us a little bit about what's happening with the sugar maples in Vermont and how they're affected by all this.
Well, I don't know a lot about them. I keep waiting for someone to go in and extract the sugar maple records and look at that question more carefully, and I have not done that. In our warm years, people have started sugaring in January, and then sometimes it's got more frozen, and then they've been able to start sugaring again later. The sugaring industry is also hard to look at over time because the technology has changed. The introduction of vacuum pumps on the lines enabled the extraction of a lot more sugar, sap from the sugar maples. And we've been able to maintain production, although it goes up from down to year in Vermont quite successfully as a result of that. So we really, I don't think, know yet how far into the future before we see a significant decline in maple sugar production. There's certainly signs that it's been moving north into Canada because their production has increased a lot.
And it seems like a lot of the sugar maples are getting diseased also.
Well, that, of course, is the challenge for our forests. There are lots of new forest pests moving across the country, partly because we transport them and partly because there's a favorable climate winter for them. Across the Rocky Mountain West, there are 3 types of beetle that used to be killed by cold winters that survive now, and we're losing a lot of the high-level pine and forests in the conifer forests. We don't know what's going to happen to our forests. People are watching those things, watching the pests, watching, say, the emerald ash borer, and the various, there's something for the spruce. It's not my field, so I can't give you much detail on that. You need a forester to come and talk to you about that. Yes?
I'm wondering how much the variation in the tilt of the Earth affects these climate changes. Because I've read in the past the various phases that the Earth has gone through has, in fact, been affected by that variation.
Right.
So
the Earth has a lot of 3 types of variability on its axis. One is it's tilted, the axis tilted, and that's why we get summers and winters, and why we have tropics of Capricorn and Cancer. That's the tilt of the Earth's axis. And that does. So the Earth rotates around that every, I think it's 23,000 or so years. And the angle changes a bit with time, and the Earth's orbit around the Sun is not round, is not a perfect circle, it's an ellipse. And right now we're closest to the Sun in winter in the northern hemisphere, but it's not warmer because the Earth is also tilted away from the Sun in winter. But over a longer period of time, and I can't be sure, I think that one varies on a 40,000 year time scale. So the ice ages were driven by all these changes in the Earth's orbit on much longer time scales even than that, 100,000 years. So all those things are still going on. The distinct difference now is that the change that we're in the greenhouse gases in the atmosphere is happening on a much shorter time scale, the 100-year time scale. So it's overwhelming these very long influences. If human beings had not industrialized, then in some time in the next 10,000 years, we might have gone into another ice age. But we won't. Now we're warming the Earth up by other means, because the input of what we're doing is much larger than that variability of the Earth's atmosphere axis, which basically what that did was change the amount of sunlight in summer on the northern hemisphere by quite a bit, like 10%. And when there was a lot more, those ice caps melted. Yes?
Are we having more cloudy days in Vermont now than we did in the past?
I don't know the answer to that question. I don't know the answer to that question. Do you think we are?
It feels like it, but...
Certainly this winter, we will have had, when there's snow on the ground, we generally have 10% more cloud cover on average. I could say that. Our records of cloud cover are rather poor. I mentioned I'm analyzing the Canadian data, and one of the reasons I'm doing it is it appears to be the only data set we have for 60 years which has really good quantitative cloud data. And I didn't even know that existed until 15 months ago. And it's transforming, enabling us to attempt to answer that type of question. Cloud cover varies so much over the season and so much with the synoptic weather systems that the actual answer to that I don't know. I don't know. Yes?
How accurate did the studies published in the early 70s turn out to be? I'm asking that because the people who deny the existence of climate change
Yes.
claim that all of these things are computer projections and subject to error and so on.
Well, there's a grain of truth in everything. There's a very famous article in the 70s that was in, I believe, Newsweek, that said a new ice age is coming, related to what this lady has said here. And so that has received a lot of publicity since. But that was not actually based on any detailed studies at the time. Our ability to measure climate, our very, very first climate studies were the end of the 70s, yes. And they were very, very simple at that time. The second
But did they turn out to be fairly accurate?
Yes. Well, the studies that led to a report was on one of my earlier slides called the Charney Report in '79, estimating how much warmer it would get with the doubling of carbon dioxide. That number, a few degrees, 3 centigrade, 5 Fahrenheit, has not changed in the subsequent 40 years. The second part of your question, though, is a very good one. The Earth is so complicated that even though we've improved our models for 40 years, they still show quite a spread, quite an uncertainty. And so the people who don't want to believe that anything is happening or believe we should wait another 10, 20, 30 years to see what happens still have grounds to argue that there's uncertainty in the models. There are still things that are not being modeled properly. And the Earth is so big and so complex and alive, we will never be able to model it in great detail. But it's still true we have a broad understanding of what is happening. And it's also true that if we wait, what we are doing now has a memory for the next 100 years. If we wait that 100 years, it's too late. And the example I like to give to people who think in those terms, if your teenagers come to you and said, you can't predict the future in detail, so I'm not responsible. Would you buy that argument? But that's basically the arguments being used. It's saying that until you, the scientific community, can tell me exactly what's going to happen 100 years from now, we're not responsible for the future. We'll go on doing the things the way we have done. And you wouldn't buy that argument in your own life. All the time we have to make decisions with uncertainties about the future. The future is not a known. The future is actually something we create out of our actions. In this case, out of our collective actions as a planet. Yes?
The southern polar cap, what's going on with that?
That at the moment is tightening up, and the sea ice is increasing. And that's another very complex set of things. The ozone hole over Antarctica that is still there is producing a cooling in the stratosphere and tightening this vortex. You read about the Arctic vortex. The Antarctic has a very strong vortex that essentially isolates the Arctic to a large extent from the oceans, but there's also an ocean coupling right around Antarctica that's involved at the moment. The winds in that area are increasing. We don't understand all the details. The Antarctic is very, very different from the northern hemisphere because the ice on Antarctica is a couple of miles deep at the deepest places. So it's a massive ice sheet. Think a massive mountain. 10,000 feet of ice on parts of Antarctica. So it kind of produces a very cold mountain on the South Pole, and on top of that there's this very strong winds blowing around it. It's like a tight little vortex. There are very little leakage from that. Yes?
I'm kind of discouraged about the way the United States is making decisions on the future. Do you see any other country in the world who may actually go to the forefront in making a difference here, or capable of making as big a difference?
The question was discouragement with the United States and its decisions here. Examples from the rest of the world that are more hopeful. Well, every country is making its own decisions at the moment because we don't have a global agreement. And everyone therefore can look to other countries for examples. There are certainly several examples in Europe where particular countries have made specific decisions. Germany is a good example. Recycling of all electronics, mandating that the manufacturers of many, many things will simply design it so it can be unmanufactured and remanufactured at the end. Germany's making a big push, along with other countries, but Germany in particular, towards an efficient society with renewable energy production and massive development of solar electricity and wind power and transmission systems and also working on storage issues. And it's doing that in a framework where it's also trying to shut down its nuclear power plants because of the aftermath of realization from Fukushima that they just simply were not safe in the long run. So Germany's been a leader, but no one wants to follow it because it's costing them a lot of money. And Germany happens to be one of the richest and most tightly organized, in a sense, very well developed economic and industrial system with a very supportive population that wants to make this transition. They feel morally obligated to make this transition, and they don't complain that the price of their electricity is a little higher than it is here in Vermont. They want to see it happen. So Denmark has been a leader, mostly in the wind energy development. Spain has some massive development too, but it's very patchwork across Europe. And although Europe as a whole has a much more solid policy than the United States, in many countries it's still lip service to the policy as opposed to real implementation. And then on the other end of the world, the big example is China.
Yeah.
And that China has so many, we could give a whole talk on that, it's not my field of expertise either. China went through rapid industrialization using coal. And it has incredible pollution problems, which are now, I've seen figures as high as like 1 million people a year are being affected by their simple air pollution problems in their cities. And so they're trying to deal with all of that and at the same time develop an industrial, an alternative energy system, wind and solar primarily again. But even though they have the largest manufacturing and renewable energy systems in the world now, it's still small compared with the massive amount of coal they burn. So that's open. We don't know what's going to happen there. And other countries, all of them are doing something. And you can see little encouraging spots here and there, but there has been no global agreement, and I don't see how we will reach global agreement because everyone can always blame somebody else. The countries that are poor, that have not contributed to the CO2 in the atmosphere, can blame us, starting with Britain 300 years ago. We've already burnt our fair share. They have a right to burn some too to help them out of poverty. And but we're all in this together. If everyone grows and uses fossil fuel to develop to American standards of living, it's a catastrophe. And we are certainly not showing the moral leadership. This has become a simple ethical question. Not just on a global scale, it is for us here. We are now dumping on our children and grandchildren costs they cannot possibly pay. Both, not just in terms of financial debt in our society, but all these environmental costs which they cannot possibly pay for. And we have not accepted any responsibility for that, even though it's our kids and grandkids. And I have a great-grandchild at this point. Yes?
Do you mind if I speak again? I'm sorry, but
Of course you can speak.
those of you who know me, I've been working with weatherization, home weatherization in my town of Weybridge. So my feeling is we can't wait for the federal government or all these big agreements, but we can do something in our own home. So anybody who's interested in learning about how to produce energy in your own home could see me afterwards. I'll give you my card and I can give you information on how to do this, because if we the people...
If we the people are responsible, yes.
If we move, then eventually, but we really can't afford to wait. So
we can't afford to wait. And there's no reason you should spend twice as much heating with fossil fuel when with weatherization you might be able to cut it by 30%. I don't know how many are aware of the community solar farms that have been developed rapidly in the last year. Those are just an amazing. I live in a relatively wooded area and I have delayed installing any local photovoltaics for that reason. It's cut down my forests versus that. But I just bought into one of these community farms that has just got an award for what they're doing across the country. And for an investment, I can for me investing in a solar farm, I can supply my electricity averaged over the year, and from a financial point of view, it's a 7% tax-free return for the next 20 years. And
I think we're going to have to.
we have to, yes, we are out of time. If any of you want to stay and ask more questions, discussion, go ahead. But thank you.
very much.
Thank you.